What's up, guys? It's Sig from PicoPlanet back with another quick update on my processor simulator game. So the first part of this update is that I actually have a working title for this project now. And so at least for the time being, although like it might make it to the eventual final release, I'm going to be calling it AssemBLOCKS, as it's really like a mashup of assembly language and block programming, both of which this game kind of pulls together into one to teach. So I also did want to address the delay before this update, which is due to a couple of factors. And the main delay now is that I'm back to school, so I just can allocate less time to working on the project. But it also does come with the silver lining that I got this approved as my independent study course for second semester. So I'll have like an entire period every day specifically for working on, AssemBLOCKS. But we'll have to like wait for second semester for that. So that'll be like, starting like January-ish will be about when that becomes time in my day. But then like the other more unexpected source of delay was a brick fell through my ceiling while my air conditioner was being replaced. So it unfortunately fell over my computer, and a lot of cleaning plaster dust and some parts replacement was necessary. So my computer had been out of commission for a couple weeks, and it's only just back up and running again. And while I'm doing like all these updates, I might as well give you my thoughts on the whole Unity runtime fee situation. So like I know that Unity's been in the news a lot recently because of this pricing model change. Charging developers a fixed rate per download of their game, including like re-downloads or potentially like fraudulent downloads. And so a lot of people were, like rightfully so up in arms about this situation here. But I just wanted to share my thoughts as like a small game developer. I definitely do not reach the $200,000 a year threshold, so the changes, they don't affect me at present. But it would have affected many VR game developers that are just slightly bigger than me, right? So I do not condone really changes like this, especially like retroactive changes to the terms of their service. And I think that that's really the main one that we have to watch out for. But as of a few hours before, making this video, Unity rolled back these changes, at least for their personal plan, and kind of like altered the effect that it has on pro plans. So, while for many people like trust with Unity's been broken, there's plenty of cases where projects are either like too far into development, or like locked into Unity due to compatibility. Like here, the Meta Interaction SDK that makes all of this work, like all the hand tracking stuff, the entire like grabbing system, all of that sort of thing, kind of like is Unity exclusive, at least for the time being. So that makes in many cases abandoning the engine not really realistic, as much as we don't approve of that sort of thing. Okay, so with that out of the way, moving on to the rest of this development update, the main thing I have to share here is the new workspaces system. So when editing code on a computer, it's like common to use an IDE, which stands for like Integrated Development Environment. And so it kind of makes sense to replicate this experience in Processor Simulator. And so this is kind of the first step to it. So if we look right back here, you can now switch between the machine code editor and the assembly editor UI. And that kind of like provides some separation between the two workspaces, and you can switch between them based on like what kind of program you are trying to work on, right? So I just want to demo that here by making a program that kind of shifts a bit along port B. So that'll be a pretty simple program. We could do it in either, the machine code editor or in assembly language, either one. I think I'm going to stick with assembly at least for this one. So let's go ahead and switch that workspace right over to our assembly workspace. So let's see, let's start off with loading an instruction, right? We're going to use that load instruction right here along with the absolute addressing mode, and we'll just load one 1 second. I have stuff on my desk right over this button. There we go. We'll start with loading 1 into the A register. And then what else are we going to need to do? Well, we'll need to store it out to B, right? So store A, it's absolute, so we don't really need it. It's implied, basically, if you don't put anything in there that it's absolute. We're going to put it out on 6,000, which is the like mapped position of port B on the versatile interface adapter. So 6,000. There's our store instruction done. And honestly, we could put that right there, but I think that this might be a little bit more complicated than that, so let's not get too deep in the weeds quite yet. So what might be the next thing we need to do? Well, we're trying to basically, if I grab this little visualizer here, right now when we run the program, this LED right here will light up, right? What we want is that every time the program loops, we want the LED that lights up to move over 1, right? So we're adding like powers of 2 essentially to each of our things if you think about like the 8-bit representation here. And one way that we're able to do that, at least with this assembly language, is this arithmetic shift left operator. And so that's basically going to shift new bits into this end of your register, right? And I believe that this is in the A register that it does this. And then it'll just push everything off to the right. Or I guess like off to the left, from right to left. So ASL, we're going to want to arithmetic shift left the A register, right? So let's grab out that A addressing mode and stick that right on there, and it doesn't require anything else. So we'll just keep that. And I guess it might make sense to put all of this in a loop, right? But in order to do that loop, we're going to have to somehow figure out if we want to, like continue the loop like this and just like keep going, or if we need to reset our bit back to 1 so that like it kind of continuously loops as opposed to just overflowing, right? Because what we don't really want is like to keep shifting it and then it just shows all zeros or something like that. So let's see, what can we use here? Let's use compare. So what compare will do is any value that we put after it, like any memory address or absolute, absolute value that we put in there is going to be compared to the value in the A register. And we have the same function for the X register and the Y register, but we're not using those. So let's compare these to the immediate 15, I guess. No, that's wrong. Basically, we want it to be 1, right? 0, 0, 0. Bet that'll be like hex 80, maybe? Yeah. So that's one reason why it might make sense to use like the binary thing so that you don't have to like try and convert these in your head like I just had to there, but that works. We will compare it to that. And so compare is going to basically set, it's going to set the flag. You can see if we go right around to here, here are all of the different flags available to us. And I'm pretty sure it's going to set that 0 flag if the comparisons, if they're equal. It does that essentially by subtracting. So we can then use branch if, let's use branch if equal. And we're going to branch to up here where we load 1 into the A register and basically reset the program. So let's grab out like a, not define, label. Let's grab out a label and we'll call this one reset. And make 2 of those. Okay, and I guess we can put that in our program, right? But then we're also going to want a loop, right? So let's make a label for loop as well. And that loop is going to happen after we load this in. So there we go. Now we're making some progress putting the program in there. So for our loop, we're going to want to basically branch if equal. If the value in our A register counts up enough times, basically like if it counts up like all 8 times here, 7 times or whatever, that it reaches this like hex 80 value right here, then it's going to reset back to here and then run again. But otherwise, we just want it to continue the loop because obviously like our 1 hasn't reached the end yet. So for that, I think just, a simple jump's going to work the best. There we go. It's a little bit hard with hand tracking to grab the right one. I need to spread all these out a little bit more now that I have the space with these workspaces. So then basically, otherwise, we'll jump to the loop. So I guess we can see if that's going to work maybe. So the first thing over here is we have this new console for our assembler. And so the console basically gives us all of the output of the assembler as it runs, including like errors, messages, that sort of thing. And so here you can see an example. It's showing the mnemonic, then the addressing mode, then the operand, and then basically what that converts into over in machine code land, right? So, like it's going to be that AA is like our fake translation of the mnemonic, and then BB and CC would be like the operand split up into 16 bits, little endian format. So if we hit assemble, I guess we can see if this assembles properly. All right, so I must apologize for that dirty little jump cut I did right there. But I discovered while I was working on this that there was an issue specifically with the assembler handling instructions that didn't have a operand, such as this ASLA, which posed a problem here because it was basically trying to convert between, it basically automatically detects between like this percent and the $sign, or in decimal as well. Like if we go right in over here into decimal and we type like 42, you see we have like essentially no prefix at all. It basically handles that. And so it was trying to handle that with nothing there, which was causing errors. So I just made those fixes and am running this again. So hopefully it works. You can see I just ran the assembler right there. We'll run it again in a minute, but I haven't actually tested it out over here yet. So I have a feeling it will, just because having made this program just fine before with the machine code editor, I don't think in one of these videos, but at least on my own just for fun, I'm pretty sure that this general concept, at least for the structure of the program, works. So let's first hit assemble and see what happens. So you can see it assembles stuff very quickly here. But the first thing is it reads this first line, and it stores this reset label in an array, kind of to reference later. And then it goes on, it reads that actual line of assembly code, converts it into, the opcodes we're all familiar with. It will do the same thing for the loop as it did for the reset right here, just kind of storing it away for future reference, and then continues on down. You can see converts our story into that 8D command. Then the ASLA, I just made a couple of changes here so that this works successfully. You can see that there's a space right there where you would expect the operand to go, but it's not. Then obviously any operand would be back here. And the point where you would have an operand with the arithmetic shift left command is if you were going to be comparing it to a memory address. But we're not. We're just using the A register. So that's kind of how this whole funkiness came about. But then essentially we compare this shifted over value in the A register to hex 80, or 1-bit set all the way on the left. And if it's equal, basically, if we've run out of spaces, well, then we run over to the reset function where we set our A register back to 1 and it loops through all over again. And if this fails, so this is branch if equal, if it's not equal, then it just moves on, keeps going through the program, then we jump to the loop. And so here's the loop. So how are these two things interpreted? Well, it goes into its array storage of labels. It checks for the label and checks for its like associated position, like where the label showed up in your program. And assuming that like it finds the label, then it substitutes that position with the additional offset of whatever .org you applied to it. So that's more or less how these labels work. And so you can see that like successfully right here, it's converted like our reset into, like our branch if equal. Here's our command, and then that is a relative offset to move to. So like F6, reason that it looks like that, let's go over here and just show it, go into binary. Notice how this last bit is set. This is 2's complement for negative, so you can see basically the reset is an offset that's backwards. It's a backwards offset to somewhere back here, happens to be right here. Whereas our jump command, it takes a full like 16-bit argument and is simply the place to jump to, right? And so the place that we want to jump to obviously is the loop. So if you consider the actual lines in the program right here, you can see that our loop begins right here at store A 6000, or right here 8002. And so it correctly finds that 8002 by looking it up and then converting it into 16-bit little endian. So with the assembler finished, next thing we need to do is upload it to the EEPROM. And so I have already connected our EEPROM to the EEPROM programmer, just like that. So if we go right here, press that upload to EEPROM button, you see success, program uploaded to the EEPROM. If I had this disconnected from my EEPROM programmer, well, then we'd have a failure because it doesn't know which EEPROM to connect to. And right over here, I have it currently disabled, but there's currently in the works a like computer component spawning system so that you can pick out any component you want and have it be generated. And one of those components is obviously going to be the EEPROM. So we need to be able to select which EEPROM we want our couple of workspaces to write to. So with that written to the EEPROM, I guess we can continue on now, right? And I am all twisted up in my cord, so I have to go around. There we go. I have one mic cord and my link cable cord right now. But what we're going to do is connect our EEPROM into our memory bus. We'll connect the RAM into the memory bus. Pretty sure it's not necessary here, but I might as well connect it just for demonstration purposes. We'll connect this visualizer up to port B and show it off kind of right here because it is the whole point of the program. And click all those in. Get our processor attached up to the memory bus. Reset button for the processor. We're not going to use the interrupt request button this time around. And finally, let's get the clock connected up so we can control it. And maybe in order to see the clock better, I will move all of these forward slightly. There we go. That seems pretty reasonable. Okay, one more thing. Let's do this right here. Let's put this on the memory monitor. So now we have our memory monitor hooked up. We might as well put in our 8000 for the start of the EEPROM, and then ADFF. There we go, ADFF. Fat fingers using the controllers right now. I'm not actually sure why. I might as well switch to my hand tracking. But you can see on our EEPROM right here now that we have a very pretty like short program, just like loading into the A register, storing that out onto the port B, which is at 6000. Then that 0A is going to be to if we look right over here, 0A is arithmetic shift left on the A register. And then we have 2 bytes for the compare instruction, a couple more right here for the branch if equal, and then finally in order to jump, assuming that it's not equal. So let's give this a try. I will just start manually ticking the clock, and we'll get through a couple of ticks here before we actually see anything interesting. So we're at 8,004 right now. So look, like 8,000 right here. 1, 2, 3, 4. You can see that it has read out like that entire 16 bits. And therefore we have put right out onto here our first light. So let's now turn on the clock. And it's set to twice per second, so it's just kind of going to continue along. We should see it switch pretty rapidly. So let's bump up the speed by 1. That's getting a little bit faster. And then again, there's the program running at 100 hertz, which is obviously significantly slower than the processor would normally run. We can bump it up to 1,000 hertz and reach 10% of this processor's like true speed. But let's turn that off just for performance reasons, and pay attention here. See if you can notice something. That's right, this light never lights up. And why is that? Well, let's go back and look at the code here. Notice how we are shifting to the left and then comparing, as opposed to comparing and then shifting to the left. So one thing that we could do to try and remedy this would be to move our compare and branch to before the arithmetic shift left. And so that way we would then no longer have this issue with it not showing the last value, because it would always still store one more essentially past there. And I guess if we recompiled or reassembled the program, we could see if that makes a difference here. So there we go. Now we have moved these around a little bit. You'll see the order of everything changes. And if we simply attach this right up to our EEPROM, let's stop the clock and reset the computer. Upload to the EEPROM and reset it again. Our memory monitor will have changed slightly. The reset command isn't going through to this visualizer. Not entirely sure why, but we can check up on that. And so if we turn our clock back on here, now you'll see we do get the last light showing up. And so you can kind of see how using this assembler console can kind of help you debug things. In addition to obviously the like granular control afforded to you by like manually ticking and taking a look at the readout of info. But this is also really useful because you can see exactly which address each of your lines of assembly code comes out to, and exactly the values that are showing up at those addresses. All right, so that's pretty much it for our quick update on AssemBLOCKS today. I hope that you enjoyed watching this update and enjoyed taking a look at this little bit shifting program. And finally, hope that you will stay tuned for more updates like this, and hopefully even some bigger ones in the very near future. It's been Sig from PicoPlanet. Have a wonderful day.